A user clicks buy, the money leaves the wallet, but the seat reservation fails, leaving the system in a broken state. Traditional two-phase commit protocols create performance bottlenecks by locking resources across multiple databases until every node acknowledges the transaction. Horizontal scaling requires discarding strict atomic transactions for the Saga pattern, which manages consistency through a sequence of independent local transactions. Every forward action in a Saga must have a corresponding compensating transaction that semantically undoes the effect of the initial operation. Compensation is a semantic undo, not a physical rollback. You do not restore a previous database snapshot. You execute a new inverse operation. Orchestration uses a central controller to tell each service when to execute its local transaction and when to trigger a compensation. The orchestrator must persist its own state machine to track which steps succeeded and which require reversal if a failure occurs. Choreography relies on services listening to events and deciding independently whether to proceed or trigger their own local compensation logic. Choreography can become difficult to debug because there is no central place to view the current state of a complex multi-service workflow. Compensating transactions must be idempotent. If a network failure causes the compensation command to be sent twice, the second execution must do nothing. Every Saga requires a unique correlation identifier passed through every header to ensure all operations are linked to the same business process. Store idempotency keys in a dedicated database table. Check this table before executing any logic to see if the request identifier was already processed. The check and insertion of the idempotency key must be atomic within the local database transaction to prevent race conditions during high concurrency.
In a bank transfer, the compensation for a debit is a credit. You cannot simply delete the transaction log entry due to auditing requirements. The Outbox pattern ensures that database updates and message publishing happen atomically by writing the message to a table in the same database. A separate relay process pulls the Outbox table and publishes messages to the broker, ensuring at least once delivery even if the service crashes. Because brokers guarantee at least once delivery, your compensation logic will eventually receive duplicates. This makes your idempotency logic the primary defense. What happens if the compensating transaction itself fails? You cannot roll back a rollback. You must retry until success or trigger manual intervention. Failed compensations should be moved to a dead letter queue after maximum retries, alerting administrators to investigate the inconsistent state immediately. Sagas lack the isolation property of standard transactions. Other processes can see and modify data before the entire Saga has reached final consistency. A lost update occurs when Saga A updates a record, then Saga B overwrites it, and then Saga A triggers a compensation that reverts everything. Use a state column like pending to act as a semantic lock. Other transactions check this field to avoid modifying records currently involved in a Saga. Design operations to be commutative where possible. If the order of execution does not change the final result, many isolation anomalies simply disappear. In high-stakes environments, treat all uncommitted Saga data as invisible to the user interface to prevent decisions based on potentially transient states. Attach version numbers to every record. Compensating transactions must verify the version has not changed since the original forward operation was executed.
A service might crash after its local transaction commits, but before it sends the success event. Your infrastructure must handle this crash recovery. Use exponential backoff for retrying compensations. This prevents a failing downstream service from being overwhelmed by a flood of repetitive recovery requests. Orchestrators must write every transition to a persistent log. This log is the source of truth for the system state during a total power failure. Event sourcing fits perfectly with Sagas. Instead of updating state, you append events. Compensation simply means appending a new compensating event to the stream. Some Sagas last days, like a physical shipment. Your design must account for timeouts and business-level cancellations that occur long after the first step. Standard testing focuses on the happy path. You must explicitly unit test your compensation logic by mocking failures at every single step of the Saga. Inject latency and random network partitions in your staging environment to verify that your compensation logic can handle realistic distributed system failures. Distributed tracing is mandatory. You need to see the entire span of a Saga, including the triggered compensations, in a single visual timeline. Sagas trade immediate consistency for availability. The time it takes for a system to reach eventual consistency after a failure is your compensation latency. Create dashboards that track the number of active sagas and the duration they spend in an inconsistent state before either committing or rolling back. The user interface must be designed for eventual consistency. Use notifications to inform the user if a previously confirmed action had to be compensated. Ensure your compensation logic does not trigger more sagas that could also fail. Keep compensation as simple and as local as possible to avoid recursion.
For complex sagas, use workflow engines like Temporal or Camunda. These frameworks handle persistence, retries, and state management out of the box. Run background reconciliation scripts to compare different service databases. This catches any edge cases where a saga failed without triggering a compensation. Verify permissions for compensation. An attacker might try to trigger unauthorized rollbacks to disrupt service or manipulate balances through repeated cancellation attempts. Minimize the number of services involved in a saga by grouping highly cohesive data into a single service with its own local ACID transaction. Use WebSockets or server-sent events to push saga completion or failure status back to the client instead of making the user poll. Rollbacks are expensive in terms of system resources and user trust. Design your forward path to validate as much as possible before committing. Building bulletproof compensation requires idempotency, a robust outbox for messaging, semantic locking for isolation, and comprehensive observability across all service boundaries. Mastering compensating transactions allows your architecture to scale without sacrificing the data integrity required for critical enterprise integration workflows.